My name is Sirisha Kallakuri. I'm beam diagnostics engineer at Advanced Photon Source. I mostly work on storage ring feedback systems that deal with coupled bunch instabilities and beam stability, mostly electron beam stability within the storage ring. So today I'm going to present a brief summary of our efforts in orbit feedback control for enhancing beam stability. So I'm going to cover majorly two parts. It's in two parts: feedback methodologies for unified operation of slow and fast characters in a single algorithm. I think Q&A's introduction really helps me to go through my introduction fast. So, and then we have done some work on using orbit feedback controller with an RF phase actuator to deal with the coupled bunch mode 0 oscillations. So that's a quick introduction to Advanced Photon Source. Advanced Photon Source is recently upgraded. It's a synchrotron source of high energy, high brightness X-rays. Here is the, here is our aerial view of our machine. The storage ring is basically a circular accelerator where the electron beam, while traveling, loses energy in the form of photon beam. Those X-rays will be that photon beam is directed to different beam lines. The triangular buildings you see are the beam lines where the photon beam is sent for user experiments. There are a wide variety of academic and industrial users use these X-rays for fundamental and applied research. So the main motivation for our problem here is ultra-stable orbit is really essential for most of these user experiments. So we need to stabilize the moment of beam centroid distorted by environmental disturbances. In engineering terms, the beam stability can be defined as AC RMS motion tolerances of the beam centroid, electron beam centroid traveling in the storage ring within a frequency band. Our closed loop bandwidth, we are looking into 1 kHz, and we want to control the AC RMS motion within 1.2 microns in horizontal and 0.4 microns in vertical. So for beam stabilization, we are using fast orbit feedback system. The beam position monitors are the sensors, and the dipole magnets known as characters are used as actuators. For the upgraded APS, this system is under development at present. Right now, we are going to develop a system with 560 sensors and 160 fast and 160 slow characters. The control architecture would be a little different from Diamond. We will be going for a distributed network of 20 feedback processors. Each local processor receives positional data from all 560 BPMs around the storage ring, and it provides drive inputs to the local character magnets. Here is a high-level block diagram of how we envision the closed-loop feedback system. The open-loop model is a two-dimensional process since the variations are continuous in both time and space. So we have the response matrix and fast character and slow character dynamics. Our feedback controller is a series combination of inverse response matrix and the dynamic fast and slow dynamic controllers. Our goal here is to come up with a unified feedback configuration where both fast and slow character correction can be done in a single feedback algorithm. So we are exploring different methods, the best way to do this. So so far we have developed and tested two methods for the unified operation of both fast and slow actuators. In the first method, we tried replacing the regular slow character response matrix with a subspace that is orthogonal to the space defined by the columns of the fast character, columns corresponding to fast characters in the whole overall response matrix. That way, basically, they are orthogonal to each other and would not fight if we combine the correction into the same loop. We tested this method using, since the the whole system is under development. We have a prototype system with 4 fast and 4 slow characters and 16 BPMs. That's our sensors for per plane. So we tested this method and in experiments with the prototype system at Advanced Photon Source. So you can see here I am presenting the BPM response and the fast and slow collector drive responses when a 50 micron set point is applied to 2 of the BPMs. We can see basically the fast character starts correcting immediately and the slow characters catch up. So the closed loop operation seems stable with this algorithm. That's a good start. One of the key features would though the fast characters operate all the way to DC. I can actually see that here. So this may be suitable for applications where the cost of fast input is not a concern. So we are also looking into algorithms where we can rest the fast characters in steady state. The mid-ranging is a great example and apt application for us. So briefly, in order to explore more, the experimental time is really precious. So we developed a simulation model in MATLAB and Simulink. Our main motivation, our main way of validation is we are comparing measured and model responses at different, in different conditions. And as you can see from the comparison plots I have plotted, these are the character drives and the BPM errors in different conditions. The simulator responses are in good agreement with measured data. For some of our explanatory, when exploring for some of the algorithms, we use this feedback simulation model for testing. So as I mentioned, the previous method we developed and implemented would use fast characters until DC. So if we don't want to, there are some situations where we don't want to continuously operate the fast actuators. So mid-ranging control theory would be a suitable application. But as we know, it is extensively established for 2-input single output configuration. The main design criteria, briefly, I want to mention for the mid-ranging control theory is we want a desired response from reference set point to the output, and we want desired response from fast input set point to the fast input, and we want a decoupled response from fast input set point to the output, because whatever changes we make to the fast input, that shouldn't disturb the output. So with this as a background, we tried to come up with a multivariable approach to the mid-ranging control. We didn't want to deal with this as a 2-input single output problem, since we have a multiple characters and multiple BPMs to deal with in a single algorithm. So our approach is basically rearranging the inverse response matrix with the mid-ranging concept. So basically the input to the fast feedback loop is the BPM error, and the input to the slow feedback loop is the fast character drive set points. So the fast dynamic controller basically generates the fast character inputs as in a regular way, but the slow character basically generates the drive inputs based on the fast character set point, DC set point. So this algorithm we tested in simulation in a multi-input, multi-output configuration. The configuration we considered here, I'm presenting the results. It's easier to plot when there is like 2 and 4. So I selected 2 fast characters, 2 slow characters, and 4 BPM example. So the closed loop is stable with both fast and slow characters when they're used in a single feedback algorithm. So here the responses of BPM and the fast and slow character drives for various set point changes to BPMs and the fast character inputs are shown in this in these plots. So we tested the design criteria, basically, whether the BPM position is following the BPM set point, so that the steady state error, BPM errors is 0. That's the first design criteria we tested. And then the first characters are either going to 0 or reaching their DC set point. That's the second design criteria. So in steady state, the fast character drives are basically following whatever the DC set point we set up. And finally, the decoupling between the fast character and the slow characters. So the fast character set point changes are not having any effect on the BPM error. So the next part we test, we are going through is the orbit feedback controller with RF phase actuator. So the couple bunch mode 0 oscillations basically induce horizontal orbit motion at synchrotron frequency. That orbit motion directly comes within the orbit feedback bandwidth, but the character drives cannot deal with that component because the character drives are dealing with Betatron and oscillations, that is X and Y position. So RF phase control can deal with the energy component. So we used the energy induced component extracted from the measured BPM points and are dealing with the synchrotron motion suppression. So we tested this in experiments at APS. One of the biggest interesting feature from advantage from this is we found the reduced feedback control effort during the combined operation. So because when we are only suppressing the energy component, we had to use larger character phase drive. And if we are only using orbit feedback and we are only compensating for Betatron oscillations. So when both feedbacks are running together, the energy and Betatron components are controlled together. So the feedback errors are less. So each component is not trying to correct what it cannot correct. So we got a mode orbit motion suppression with less control effort from each character and phase drives.
Sorry, just a question. Do you have Betatron feedback system in parallel?
Parallel? Yes, yeah, they're running together in the same algorithm.
Same algorithm?
Yes, yeah. So we don't want to separate the algorithm. You have to feed from. That's why I asked about the question about the interaction, because it's easier to keep them in the same algorithm. That's why we are using the phase IRM. We are using the same infrastructure, so it comes as a extra row, but physics are different. But we are feeding this drive signal to the low-level RF. It doesn't go to the character magnets, it goes to the low-level RF, but so that's why the interaction, this computation basically, all the remaining rows except the bottom row looks at the Betatron motion within the X position, and we compute at the bottom row, we use the energy component from the X position, so that they control separately, but they are running in the same feedback loop. Yeah, so I think in conclusion, initial prototype experiments with the developed methods are showing promising results, but there is a long way to go because we are aiming at the 20 feedback processes in a distributed network architecture. So we are investigating to implement as a distributed control implementation of these tested methods, and also extending the prototype simulation model to the full-fledged distributed control model. And also, and major ongoing effort now is like we are spending most of our time in developing the actual system for the user operations. I think that is all I have, and I really want to thank all the awesome people listed here for their great contribution and support in all this work.